I'm not talking and nobody hears me.
Yes.
Yes.
Okay, thanks. So let's start by answering the question, what is grounded cognition? What grounded cognition is can perhaps best be understood if it is contrasted with an opposing view that was quite widespread in the cognitive science in the latter half of the 20th century and still has many proponents to this day. According to this view, the higher cognitive competences, which include things like language, reasoning, planning, problem solving, etc., so the hallmarks of human cognition, so to speak, that these cognitive competences can best be explained as the algorithmic processing of so-called amodal symbols. So what does this mean? Algorithmic processing means that these cognitive competences are explained by appealing to a computer metaphor and to computer or Turing machine-like mechanisms that operate on symbolic representations and do some deterministic perform some deterministic algorithm on these symbols. Now, importantly, these symbols were believed to be amodal, which means that they bear no resemblance to what they stand for. This is perhaps best understood by an example. So in a reasoning task that's often given to participants in psychological studies, participants are provided with premises that specify some state of affairs. For example, the Porsche is parked to the left of the Dodge and the Ferrari is parked to the right of the Dodge. And then they are asked to verify whether or not a given conclusion follows from these premises. And according to the classical amodal symbol systems view, humans solve such problems by transforming these phrases into a logical representational format and then to try to deduce the conclusion from the premises using some algorithmic proof system. And these symbols are called amodal because the meanings of the words like Porsche, Dodge, and Ferrari, etc., have no effect on the reasoning. The reasoning is completely detached from perception or from the perceptual or conceptual meanings of the symbols. And in the last decades, it's been increasingly recognized that this classical cognitive science view is extremely problematic. For instance, there's no empirical evidence for algorithmic processing of amodal symbols in the brain. What we find instead is that the higher cognitive processes are grounded in the sensory motor regions of the brain. So grounded means that the sensory motor regions, which are responsible for perception and motor action, also are involved in the higher cognitive competences. For example, we find that the same brain regions which are involved in the perception of objects of a given category are also involved in reasoning about objects of that same category. So, for example, somewhere in my brain, I have a region that is used when I categorize something as a tree. And fMRI studies show that this region, or at least a very close by region, is also used when I imagine trees or solve some abstract reasoning problem about trees. Another problem with this amodal symbol systems view is that it is inconsistent with neural principles of computation, because these computational models are often given as computer programs, which involve things like function calls, random access memory, etc. And it is not clear how this could be realized by the neural hardware of the brain. So neurons can do no such thing as calling a function or accessing an address in some big memory store. So the random access memory of a computer is not at all how memory works in the brain. In response to such problems, views of grounded cognition emphasize instead that the higher cognitive competences rely on perceptual or motor simulations that use the same brain regions that are also used in perception and motor action. So to come back to our reasoning example, a hypothesis put forward by Ragni and Knauf and verified in experimental studies is that when humans solve reasoning tasks, they build so-called spatial layout models. So, for example, when they encounter the phrase, the Porsche is parked to the left of the Dodge, what they do is they create some perceptual representation. Sorry, I have to close the window shortly. What they do is they create some perceptual representation where they embed a Porsche to the left of a Dodge. So this here is actually a neural field model of this Ragni and Knauf idea, where the various objects mentioned in the premises are represented as peaks in a neural field, which bear the specified relationships to each other. And then the same for the second premise. Here, the Ferrari is parked to the right of the Dodge. This existing spatial layout model is extended by embedding a Ferrari into that same representation in accordance with the mentioned relationship. And then the idea is that the conclusion is simply read off from that spatial layout models. So we can then check whether the Dodge is parked to the left of the Ferrari simply by checking whether this is in fact true in this given spatial layout model. So in other words, when we hear language, we build a model of what's mentioned in the language, and then we use that model to make inferences. And this is not just true for spatial language. So even with abstract relationships, like Willy Brandt was more popular than Gerhard Schröder, humans also build spatial layout models, which has also been demonstrated by a range of studies. And this logical reasoning problem, which seems to be a hallmark of abstract reasoning, really can be solved using a relatively simple spatial layout model. So you hear this premise, Willy Brandt was more popular than Gerhard Schröder. So you embed representations of Brandt and Schröder into some spatial representation that represents some abstract popularity space. And you do the same with the other premise. And then again, you can read off whether the conclusion that Willy Brandt was more popular than Angela Merkel is true simply by looking whether the representation of Merkel is to the left of Willy Brandt in this abstract popularity space. A final observation that I would like to note comes from the study of language, in which Lakoff and Johnson and Hofstadt and Sender, for example, have really analyzed large corpora of language and pointed out that many of our abstract concepts are metaphorically related to more basic concepts. And these basic concepts are often spatial in nature. So for example, we relate our concept of happy to our concept of up, and we relate our concept of sad to our concept of down, and we somehow make sense of happiness and sadness along some spatial dimension between up and down. Such observations may then lead to the hypothesis that many of our abstract concepts supervene on visual spatial concepts. And this motivates why in TFT emphasis has been put on building models of visual spatial cognition as a means towards models of higher cognition. So the idea is if we first build models of spatial language, like language that involves spatial terms like above, below, to the right, or visual features like red, green, blue, or shape categories or things like that. And we demonstrate how such reasoning problems can be solved in these spatial dimensions, then we can later extend those same models towards more abstract reasoning tasks. And that is why I'm now going to present various spatial language understanding models. Before I can do that, I need to provide some background from the field of cognitive linguistics. Cognitive linguistics is a field of study that combines knowledge from various cognitive sciences, most prominently linguistics, psychology, and neuroscience, in order to infer the mechanisms that underlie language understanding and thought, which are often taken to be equivalent. So language understanding is often assumed to be the process by which we think the thought that is communicated by the sentence. So the idea is that when I utter a sentence, then this sentence expresses a thought. And when you understand that sentence, you do so by virtue of thinking the same thought or a similar thought that I was thinking when I uttered the sentence and that I intended to communicate with the sentence. A common stance from cognitive linguistics is called conceptualist semantics, according to which humans understand a word by virtue of possessing a concept denoted by the word. So for example, they understand the word tree by virtue of a tree concept. That is some mental representation that characterizes what a tree is, and that is used by all of the cognitive competences that somehow need knowledge about trees in order to work. So understanding sentences that involve the word tree, for example, or categorizing something as a tree, or imagining trees, or exhibiting appropriate behavior towards trees, for example, cutting them with an axe, or solving some abstract reasoning tasks that involve trees. Similarly, we understand prepositions like the word below by virtue of a relational concept. That is some mental representation that characterizes what it means for an object to be below another object. According to prototype theory, concepts are long-term memory representations of a prototypical instance of the category. So the idea is that our concept of a tree is a prototype, which is a long-term memory representation that is involved in the various cognitive competences that I just listed: understanding the word tree, categorizing, imagery, reasoning, and behavior. And there are various ways to spell this out. There's a particular way that prototype concepts are implemented in DFT. But on a more abstract level, you can think of a prototype as some mental representation that somehow captures the essence of trees, and that could be conceived of as something like a blend of all the possible trees, or all the trees that were involved in learning what a tree is. Another important idea from cognitive linguistics is referred to as compositional semantics, according to which humans understand a phrase by activating the concepts denoted by the individual words and combining those concepts in accordance with how the words are arranged syntactically in the phrase. So to give you an example, in the phrase "a black swan below a tree," compositional semantics would state that first of all, we activate the concepts associated with the individual words. So some concept of blackness, some concept of a swan, concept of below, and the concept of a tree. And then we combine these concepts in order to determine the meaning of the whole phrase. Now, importantly, this conceptual combination process must respect how the words are arranged in the phrase. So there's a difference between a black swan sitting below a tree and a swan sitting below a black tree, even though they contain exactly the same words, but these words are arranged in a different way. So we somehow take these representations of the concepts and some representation of how they are arranged in the phrase in order to arrive at an interpretation of the whole phrase. Another notion that will be important for the rest of the talk is the concept from linguistics called a noun phrase, which is a phrase that describes an object, loosely speaking. Examples are the tree, or the small tree, or the tree to the right of the house. This is called a noun phrase because it contains a noun, in this case tree in each case, and additionally it might contain adjectives or prepositional phrases like to the right of the house, which specify essentially where the tree is. So the whole thing is still a noun phrase, the tree to the right of the house, but this noun phrase as a whole contains a prepositional phrase to the right of the house. An important property of noun phrases is that they can be nested. So to look at an example, we can see, we can take the noun phrase, the tree below the lake, and insert it as the object of a preposition in order to form the more complex noun phrase, the tree to the right of the tree below the lake. We can also conjoin noun phrases. So we can form the noun phrase tree below the lake and above the house. And don't be confused by a tree, what it means that a tree is below a lake. We're talking about an idealized scenario here where we are looking at a map from above, and the tree below the lake would be this, for example. And we can imagine that there are many possibilities in which we can arrange the various objects grammatically to form all kinds of different object descriptions. The final piece of background that I have to provide before we can finally actually look at a model is the idea of conceptual structure put forward by the linguist Ray Jackendorf. Conceptual structure is a hypothesized cognitive representation that characterizes the meaning of a language phrase as a combination of concepts. In the case of nested noun phrases, the conceptual structure must specify which objects there are, which concepts characterize them, and which relationships hold among the objects. So the idea is when we hear a natural language phrase, a natural language processing system transforms that phrase into a representation of its conceptual structure. And in the case of nested noun phrases, we need to specify which objects there are. So this can be visualized as a graph like this. So each box corresponds to one object. There's a tree, there's another tree, there's a lake, and there's a house. And each arrow corresponds to a relationship between two objects and is labeled by the relational concept that characterizes that relationship. So for example, the first tree is to the right of the second tree, and the second tree is both below the lake and above the house. And we can see that this conceptual structure encodes the logical meaning of this nested noun phrase while abstracting away from the concrete words that were used to express it. So I will now briefly sketch a few landmark models of grounded cognition in the DFT research community. I've been told that Professor Schöner already presented these models to you. That's why I'm only briefly have a look at them. And also another reason why I'll be brief is because these models are really contained in a larger model that I will present later. So the first model along these lines was by Lipinski et al. 2012, and that model solved some spatial reasoning tasks that pertain to a single relationship between two objects. So for example, you could ask the model, where's the green object relative to the red object, and provide it with some arbitrary input image, and the model would respond that it is to the right. Or you could also ask which object is above the blue object, and in this case, the answer would be the red object is above the blue object. And this is the model. This model is essentially a part of a larger model that I will present later, so I'm not going to go through it now. Just mentioning it for historical reasons, essentially. An extension of this model has been proposed by Richter et al. 2014. And that model was able to ground a noun phrase with a single prepositional phrase. For example, the red object to the left of the green object. So no nesting really, but only one object which is characterized by a relationship to a single other object. And we can see, if we consider this image, that this requires a form of autonomous hypothesis testing. And that is because we do not know which green object is referred to. So, but we can only attend one object at a time. And that's why we first need to make a selection decision. For example, we could first select this as our green reference object, and then check whether there's a red object to the left of that green object. And if we see that there is none, we have to undo that selection decision and select another candidate. In this case, this green object here. And then we see that there is in fact a red object to the left of that green object, which is the object we were looking for. And again, many parts of this model are included in a larger model, so I will only briefly mention the most important additions to the Lipinski model, namely a process organization system that organizes the various searches. So first we need to search a reference object, then we need to search the target candidates, and if we have successfully found the target candidate, a condition of satisfaction becomes active. But if we're not successful, then we need to restart a reference process and select a new reference object. And using an inhibition of return mechanism, we have to make sure that the model doesn't select the same object again. Okay, so now comes the model that's really going to be gonna take the remainder of this talk, because it takes a long time to present. And that is a model that I developed with Professor Schöner, which serves to search, or which is a model of how we can search the object that is referenced by a given nested noun phrase in the visual input. So the model can be provided with an arbitrary nested noun phrase, like, for example, this is a very absurd example, but it's been chosen like this on purpose because it's a borderline case of what human beings might be able to understand. The tree to the right of the tree, which is below the lake and above the house. And the task of the model is to perform a search in a visual input which identifies the described object. In this case, we see it has identified this tree here, which is to the right of that tree, and that tree is both below the lake and above the house. So we can see that this is the correct solution, or the correct denoted object by that phrase. Now, this seems to be a rather absurd thing to model, but the motivation for this model is of a more general nature. And that's because this model may serve as a blueprint for other models that understand other grammatically complex language. And that is because it already solves many of the challenges that any such model must solve, and therefore comprises a huge step in this direction already. So first of all, it needs a link to the sensory input. It needs neural representations of concepts. It needs neural processes for combining concepts. It needs neural processes for relational reasoning. And it needs a neural short-term memory of conceptual structure. We're going to take a look at each of these in turn. This is the overall model. And I'm going to take you through the model step by step now. So the first challenge that we have to solve is to come up with a way to represent conceptual structure in a neural short-term memory. And so the idea is that the nested noun phrase is represented in terms of its conceptual structure in a short-term memory. And this short-term memory then is used by a compositional search mechanism to identify the arrangement of objects that is correctly described by this conceptual structure. So let's go through this example again. We find an object here, which is characterized by the tree concept, and that object stands in a relationship of rightness to this other object, which is also characterized by the tree concept, and that object is both below a lake and above a house. So we can see that this arrangement of objects here is in fact the grounded meaning of this conceptual structure here. Now, any neural short-term memory of conceptual structure must address what's referred to as Jacobs challenges, which have been put forward as challenges for a cognitive neuroscience of language by the linguist Ray Jacobs, who is also the inventor of conceptual structure. One of these challenges is called the problem of two, and is exemplified by the phrase, the small tree above the big tree. The challenge is, how may a neural short-term memory encode that there are two trees where one of them is small and the other one is big? Why is this a challenge? Well, classical connectionist models would just have a single tree node somewhere, which they would activate, but this cannot encode that there are two different trees. And it also cannot encode that one of the trees is small and the other tree is big. You cannot simply activate a small node, a big node, a tree node, and another tree node, because there's no such thing. So you need some way to bind the representation of small to a representation of tree, and to bind a representation of big to another representation of tree. Another one of Jacobs' challenges is called the massiveness of the binding problem, and is exemplified by the phrase, the lake above the tree above the house. The challenge in this example is, how may a neural short-term memory encode that there is a single tree which enters into two different relationships, the lake above the tree and the tree above the house. Now, you cannot simply encode two different relationships like lake above tree and tree above house, because this wouldn't specify that we're talking about the same tree in both relationships. And that is why it's called a binding problem, because it requires the possibility to bind a single representation of a tree to two different relationships. And this binding problem is called massive, because there's quite some flexibility in how many relationships you can bind a single object to. In order to address Jacobs challenges, we assume that a language preprocessing system, which we actually have modeled, but which I'm not going to present today, embeds objects into a discrete index dimension. So for example, in this phrase, the first tree gets an index of 1, the second tree gets an index of 2, the lake an index of 3, and the house an index of 4. This index dimension may then serve as a binding agent, which enables a neural short-term memory to encode which concepts characterize a given object. For this purpose, we introduce an object concept field, which is defined over a discrete object index dimension and a discrete concept dimension. Now, I think this is the first time that you're actually seeing an example of a discrete neural field. So a discrete neural field is almost like a regular neural field, except that you have a discrete rather than continuous dimension. So you can't have intermediate values like 1.5 or so. You can only have either 1 or 2 or 3 or 4. And this is why the lateral interaction kernel is replaced by a sum over each pair of discrete locations in the field, but the rest is exactly the same. Now this object concept field, again, is defined over the object index dimension, so the dimension along which we embedded each object, and a discrete concept dimension, where we have one possible value for each of the concepts that we account for. A peak in that field at a certain location encodes that the object with the respective index is characterized by the respective concept. So for example, this peak here encodes that the object with index 1 is characterized by the tree concept. And this peak here encodes that the object with index 2 is also characterized by the tree concept. This here, that object 3 is characterized by the lake concept. And this here, that object 4 is characterized by the house concept. So we can see that this activation pattern encodes the objects from this exemplary conceptual structure that I flashed. Not yet the relationships, but only the concept that characterize the individual objects. Here we see a different activation pattern in the same field, which shows how the problem of 2 can be solved. Namely, simply by keeping the two representations of the two trees apart. So the first tree is object 1 and the second tree is object 2. And object 1 additionally is combined with small, and object 2 additionally is combined with big. And therefore, taken together, these peaks encode that there's a small tree and there's a big tree. And this this could not be achieved without such a binding agent, because if we just activate small, big, and tree, then we wouldn't be able to distinguish between a small, big tree or a small tree and another big tree. Sorry. Now, in order to address storing the relational dependency structure in short-term memory, we also assume that language preprocessing embeds the relationships into an index dimension. So the first relationship, the tree to the right of the tree, in this example gets an index of 1. The second relationship, the tree below the lake, gets an index of 2, etc. This relationship index can then also be used as a binding agent, which enables us to bind objects to relationships. Now, a relationship has two different roles, and therefore we need two fields, these two fields here, one for the target role and one for the reference role. Sorry. To drink something. A peak in the first field encodes that the object with the respective index is the target object of the relationship with the respective index. So this peak, for example, encodes that object 1 is the target of relationship 1, which can be seen here. So we have this object here, which has index 1, and that is the target of the relationship, the tree to the right of the tree, which has index 1. And analogously, this peak here encodes that object 2 is the target of relationship 2, and this one encodes that object 2 is also the target of relationship 3. So we can see that this allows us to specify that a single tree, the tree with index 2, is the target of two different relationships. The tree is below the lake and also above the house. Now the reference relationship field does the completely analogous thing for the reference role. So for example, this peak here encodes that object 2 is the reference object of the relationship with index 1. So here this encodes this, that object 2 is the reference of this relationship with index 1. And finally, the last ingredient for the conceptual structure is a field defined over the discrete relational concept dimension and the relationship index dimension, where a peak encodes that the relationship with the respective index is characterized by the respective relation concept. So here R for right of. This peak then encodes that relationship 1 is characterized by the right of concept, which is this aspect here. So this relationship here is characterized by the right of concept. Now, taken together, these 4 neural fields that I just presented can encode the entire conceptual structure in a neural short-term memory. The next challenge that we had to solve was to bind this short-term memory of conceptual structure, or not to bind, but to couple this short-term memory of conceptual structure to a DFT model of compositional search, which identifies an arrangement of objects in the visual input that is correctly described by this conceptual structure. And the compositional search model is depicted up here. I'm not going to address this right now. First of all, I'm going to address the interface between the conceptual structure, picked down here, and this search system. And from there, we're gradually coming closer to the search system. So for this, I prepared a video. So the first ingredient is a target production field, which is defined over the object index dimension and makes a selection decision which object to find next. So in this example, it has selected object 4 for search. When an object has been selected in the target production field, the model needs to look up which concepts characterize that object. So in order to find object 4, we need to know that object 4 is a house. So here we have this object concept field, and that provides sub-threshold input to another field, which is also defined over the object index dimension and the concept dimension. And that field receives a slice input from the target production field. When these two inputs overlap, the field forms a peak. So this is the completely analogous mechanism that you're used to from visual search, where you provide a rich input along some feature value in order to highlight the spatial locations of objects with that feature value. Here we're doing the same thing, but this time we're providing rich input along a certain object index in order to highlight the concepts that characterize that object index. And this peak is then read out into a one-dimensional concept production field, which triggers a model of visual search to search for a house in the visual input. And we can see that it does this. It selects a house. And since this house is in fact the correct referent for object index 4, we know that we have found object 4 and we can store its location in a mental map. So the mental map is a field defined over the two spatial dimensions of the visual input and an additional discrete object index dimension. And this way it remembers the spatial locations of the objects that we have found already. In this case, it remembers that object 4 is at this location here, which would correspond to this location in the visual input. After having found this object, the target production field is inhibited by a process organization system that's not depicted here, allowing that field to form a new peak. Now, there's an inhibition of return field, which ensures that the same target index is not selected for search twice. So that serves as a short-term memory and remembers all the selection decisions made by the target production field. And through inhibition to that field prevents the same selection decision to be made again. So now object index 3 has been selected for search, and by analogous mechanisms as before, the concept production field forms a peak on the lake concept, because this is the concept that is stored for object index 3 here in the conceptual structure, which then in turn triggers the visual search system to search for a lake, which it finds and again stores in the mental map, this time at index 3. So now we have already found the house with index 4, and the lake with index 3, and we have remembered their locations. Next, the target production field selects object index 2, and as you can see in the conceptual structure here, object 2 is characterized as being both below the lake and above the house. And given that we know the locations of this object 3 and 4, we can now use those locations in order to efficiently find an object that is stands in the correct relationship to these two objects. For this purpose, we now need to look at the relational dependency structure. So remember, we had the target relationship field, the reference relationship field, and the relationship concept field. We also introduce a target relationship production field, which receives subthreshold input from the target relationship field. And additionally, that field also receives a rich input from the target production field. In effect, that field then highlights the spatial locations, the indices of all the relationships in which object 2 occurs as a target. So in this case, object 2 is the target of relationship 2 and of relationship 3. And so this field forms a peak for relationship 2 and 3. And this then leads to a selection decision, which is read out in the relationship production field, which reflects a decision to now process the relationship with index 2 next. And processing that relationship means we need to look up what's the reference object of that relationship and the relational concept that characterizes that relationship. And for this purpose, the relationship production field projects into the reference relationship production field, which reads out the reference object using the same mechanism that we've seen 2 times already now, and projects in a reference production field. So in effect, the reference production field thus forms a peak on the reference object of the currently active relationship, in this case, object index 3. And that's because this relationship with index 2 here that is currently active has object 3 as its reference object. And an analogous mechanism causes the relational concept production field to make a selection decision for the below concept, because relationship 2 is in fact characterized by the below concept. So effectively, the search system has now been triggered to search for a tree which is below object 3. And recall that the location of object 3 has been remembered in the mental map. So this now allows us to provide a guided visual search for objects that are below object 3 and that are characterized by the tree concept. And we can see that a spatial selection bias field highlights the area below the location of object 3, the lake, and also highlights trees. And one of these is then selected as the target candidate. And this happens to be the correct target candidate, because what the model does next, what we can't see in the current simulation, is that it checks whether this target candidate is also above the house, so above object 4 from the mental map. And since this is the case, the model knows that it has found a tree which is both below object 3 and above object 4, which is in fact the correct location for object 2, the tree which is below the lake and above the house. So that object is now also stored in the mental map, this time at index 2. And finally, we can do the exact same thing as before in order to find object with index 1, namely the tree which is to the right of object 2. So again, the concept production field forms a peak on the tree concept, the reference production field on object index 2, because object 2 is the reference object, and the relational concept production field forms a peak on the right of concept, which encodes that the model should look for a tree which is to the right of object 2. And again, the spatial selection bias system now looks for objects which are to the right of object 2 and are also characterized by the tree concept, and correctly selects the candidate for this object here. And this object is now the final result, namely the tree which is to the right of the tree that's both below the lake and above the house. Okay. The last thing that I want to briefly sketch is, last thing I'd like to briefly sketch is how the search mechanism is implemented. So I've only shown you how the search mechanism is orchestrated by the conceptual structure. But this search mechanism is almost, I wouldn't say almost identical, but it contains many of the concepts that you've already seen. So the concept production field projects to various feature fields. So for example, the tree concept projects to a tree shape region in a shape category field, and to a green region in a color field. And this then projects into attentional fields for these feature dimensions, which receive input from a perceptual system, as you've seen numerous times already, where each field is defined over the spatial locations of the visual input and an additional feature dimension. And in effect, when the tree concept becomes active, these fields form peaks on the locations of all the objects that have the desired feature values. And these are then read out and provide input into a spatial selection bias field, which then highlights all the trees in the visual input in this example. There's also a relation detection mechanism, which consists of a reference field and a spatial relation field and two neural coordinate transforms. One of these transforms converts the peak in the spatial relation field into a coordinate system that's centered on the reference object and projects into the spatial selection bias field as well. And this way it highlights all the locations that stand in the given relationship to the reference object. So this creates this cone here that highlights all the locations above the center in this example. Now, all of these selection biases are then summed up, and they provide input to a target candidate field, which selects a candidate for the object that we're looking for. And when such a candidate has been selected, it is again checked whether all the relationships hold. So in our example that we've seen, the model has to check if the target candidate is both below object 2 and above object 3, I think. And this is orchestrated by a process organization system, which first selects a target candidate, then checks if all the relations hold. And if this is in fact the case, a commit process becomes active, which then provides boost to an intermediate field that stores the location of the target candidate in the mental map. So in our example, what's relevant is this index space mental map, which is defined over the two spatial dimensions and an index dimension. And if this commit process becomes active, that field then forms a peak at the spatial location of the target candidate and the respective index that we're currently searching for. And this way, the location of the target candidate is remembered. And when that is done, a proceed to next target process becomes active, which causes the target production field, so this field here, to select the next object for search. I think I've addressed everything. Okay, yeah, I'd like to end this here. Thanks for your attention, and feel free to ask your questions.